Okay, بسم الله الرحمن الرحيم. والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone. Uh, Finally control. Okay, just in time. So just 20 lectures of preparation. So today, inshallah, we're going to be seeing that hopefully the things that we covered all leads to this point. Okay, so how do we do control of a dynamical system that lives on a manifold? Today, we're going to be seeing the first of that, not the last, of course, but again, you're going to be seeing how we're going to be using these different tools. I cannot stress enough that we're going to be needing everything we discussed. Okay, so today we're not going to be talking about manipulators, so that part is not included, but still we have the rigid body dynamics and everything that that we needed before, all of the differential geometric tools and all of the stability analysis all of the stability tools that we did afterwards, except for one last, actually the most powerful stability result that we need and we're going to be discussing today, which is Lassalle's invariance principle. But let's start as usual with the recap of last time. Today's lecture, also the next one, are very, very technically involved. Okay, and by technically involved, I mean there's a lot of math, there's a lot of technical details. So even if you don't get everything during the lecture, you really should follow all of the line of thought, just the line of thought throughout the lecture, and all of the math, you need to do it step by step at your own pace. Okay, so just we're still with nonlinear dynamical systems of this form, where x dot is equal to f of x is the one that we're talking about. X lives in a manifold, and we're looking at x dot is equal to f of x. So this autonomous system without any control, assuming we already chose what the controller is and we're studying the closed loop stability of the equilibrium points of the system. And Lyapunov's direct method allows you to do that. So if x star is an equilibrium point of the system, you can prove that x star is stable, asymptotically stable, or globally asymptotically stable, provided you can find a Lyapunov function such that it has 0 at this equilibrium point and it's positive everywhere. So we're saying that this means it's positive definite inside of a neighborhood of this equilibrium point. And if you can show that the rate of change of this scalar function along the trajectories of the system, x dot is equal to f of s, if you can show that they are negative semi-definite, the rate of change of this function is negative semi-definite, then you can prove stability. If you can have a stronger notion that you show it's negative definite, means that it's always decreasing and there's no points where that it has values equal to 0, then we can show stability, local asymptotic stability. And if you can we can prove as an additional condition that v of x is radially unbounded, which means that it's globally positive definite, then we can conclude global asymptotic stability. We said that negative definiteness of d dot is not an easy task. Okay, you can always do it in toy problems, but when you come to mechanical real life problems or the type of systems that we're interested in, mechanical systems and robotic systems, this is not an easy task. We're going to be seeing today how to do it in practice. The local definiteness, we talked about it in more detail, that by approximating v, this Lyapunov function or its time derivative, a lot in a local neighborhood of the equilibrium point, by this quadratic form where h v of x star is called the Hessian of this function, then by just looking at the eigenvalues or the positive definite of this matrix, which in the end is just an n by n matrix, even if x lives in an n-dimensional manifold, it's well defined in a local chart, then we can show that locally we have local positive definiteness or positive semi-definiteness or negative definiteness or negative semi-definiteness of the function we're interested in. And this is just a basic result from what's known as Morse theory, which is the topic by its own. We said that how do we compute v dot? We said that in general we have this geometric formulation, which is more than what we need. Okay, at least if you only talk about Rn, you've probably never seen this before. But today we're going to be seeing that when we start looking at a manifold, we do need this extra piece of information. You all know for now that x dot is a tangent vector on the manifold, and v dot is given by the lead derivative of v along the vector field that defines the dynamical system. And this is defined as the pairing between a covector and a vector. This covector dv of x is actually called the differential of the scalar function. And simply, if depending on, of course, on the manifold we're talking about, this pairing will change from manifold to manifold. The more common case that you've definitely seen this before is that if you have the manifold is Rn, and in that case, x dot is a vector in Rn, and dv of x is a covector at Rn. And simply this covector, we can write it as this row vector, just putting all of these partial derivatives of v with respect to x1 and x2 and up to xn in this row vector. And you're more familiar not with this covector version of the differential, but what's known as the gradient vector. And this is usually what you've seen before, that the partial derivative of v with respect to x1 put in a column vector form. This is known as the gradient, and we're going to be denoting it by the nabla v. So nabla v and dv, they are different things. Okay? One is a vector and one is a covector, and both are dual to each other. In Rn, it's as simple as transposing one another. But again, you're going to be seeing that in general, this is not as easy as just transposing one vector into a covector. Any questions so far on what we discussed? Brief questions.
I have a thought, say, finding the Lie algebra.
The Lie algebra. The Lie derivative is this definition.
But for a given manifold, how do we get this?
Yeah, exactly. So for the given manifold, you know the pairing between a vector and a covector, and then you can define, you can let this covector eat this vector, and this is by definition what's called the Lie derivative. The Lie derivative is a much more fundamental object in differential geometry, and it's used in different cases. For example, who here is familiar with controllability and observability? Okay, how do you do controllability and observability for a system on a manifold? Use the Lie derivative, okay, and you use it recursively, okay, so just as a side note, okay. Give you a scalar, that's right. Yeah. It's v is a scalar function, right? It eats x1, x2, x3 up to xn and gives you one number in the end. The partial derivative of v with respect to x1 is another function that goes from Rn to R. This one? Yep. After it eats x, you see here, this is after it eats x. Then you get this one. Okay. I think I see what you mean. This is the covector. You still need to multiply it by an n by 1 vector to get this number you're talking about. Is that your question? So this is a 1 by n. It's a row vector. How do you convert a row vector to one number? You multiply it by a column vector of the same dimension. What is this column vector that I multiply this and get a scalar number? It's x dot in this case. So you see, this is a row vector and this is a column vector in the case of Rn. So when you multiply this row vector by this column vector, in the end, you're going to get the scalar number, which corresponds to the rate of change of v along x. Of x is one covector that looks like this. So dv of x is one covector that looks like this. It will eat x dot. Yes, exactly. By the way, and we're going to be seeing something hopefully today in this direction. It's not necessarily that it eats x dot. It can eat any vector. But of course, on the left-hand side, the thing will change. To give you an example, when we looked at the velocity vector, and we multiplied, we paired it with a wrench. Sorry, the twist vector, and we paired it with a wrench. What did we get as the scalar? Power. We got mechanical power. When we paired the same twist with the momentum, what did we get? If you go back, you're going to find we got twice the kinetic energy. So the kinetic energy is the pairing between the momentum or half the pairing of the momentum with the twist. So in general, a vector or a covector, you can pair it with different things. It lives in this space while x dot lives in Rn. Okay. Any more questions along this side? Perfect. So Now let's look at Lassalle's invariance principle. This is a very powerful result and a very fundamental result. Who here saw this before? 1, 2, 3. Only 3? Very good. So this is new for most of you. The best thing about Lassalle's invariance principle, first of all, it's not something alternative to Lyapunov's theory, to Lyapunov's direct method. It's actually something that's augmenting. So when you do Lyapunov's method, when you do Lyapunov's direct method, and then you want to extend it further, you can use Lassalle's invariance principle. So this is one nice thing about it. So it's not an alternative theory. It's just some extra results, some extra analysis you can do. And it will allow you to conclude asymptotic stability, and sometimes even global asymptotic stability, if you only have V dot to be only negative semi-definite. So this is very powerful result. And this is usually what we get from in practice, and usually what we're going to be getting if V is actually a mechanical energy, as we saw earlier. Before talking about what the Lassalle's invariance principle is, let's talk about the concept of an invariant set. The invariant set, a set M, is an invariant set for a dynamical system if every system trajectory that starts from a point in M remains in M for all future time. It's as simple as this. Okay. What is the example, the typical example that we know about an invariant set? The equilibrium point. This is the most simple one. If I start at the equilibrium point, what happens? I always stay there. So the equilibrium point is 1 point, and you remember I can consider a set considers of this 1 point. Then this is an example of an invariant set. What about the domain of attraction of an equilibrium point? You remember what the domain of attraction is? It's a set, local set around the equilibrium point. If the equilibrium point is locally asymptotically stable, it means that if I start anywhere in this region, I'm going to, after some time, converge to what? To the equilibrium point. This domain of attraction, if I started inside of it, what happens? I always remain inside of it. So this is an example of also an invariant set. And of course, the trivial case is the whole state space. If I start anywhere in the state space, I stay in the state space. So this is the trivial example. So if I have a rotation matrix that starts in SO3 and it evolves in time, where do I stay? In SO3. I never go to R3 by 3, even this is a bigger set. Now let's see Lassalle's invariance principle. Let X star, which is a point in the state space, be an equilibrium point of the dynamical system X dot is equal to f of X and T. And assume that there exists a smooth Lyapunov function. Everything we're doing is smooth. We're not talking about, because we're taking derivatives, right? This is why we need the manifold structure. We cannot talk about it in general. So we need smoothness and we need differentiable properties. So V of X, we assume is smooth, which means that's infinitely differentiable. We have infinite number of continuous derivatives. V of X, we have this smooth function such that in some neighborhood, we're going to be calling this neighborhood capital omega of this equilibrium point in the state space, we have these 3 conditions. The first one, V is positive definite. The second one is V is negative semi-definite. With only these 2, what do we conclude? The equilibrium point is a stable equilibrium point and nothing else. The extra conditions are, let R, so we're going to be defining some subset of this neighborhood of X. This subset is all of the points X, all of the points in the state space, such that V dot is equal to 0. Exactly equal to 0, not less than or equal 0, only the points equal to 0. So in this neighborhood, we have V dot having 2 values, either something negative or 0. So we have these 2 points. If we only take the points that satisfy V dot is equal to 0, then we call this set R. And let M be the largest invariant set in this set R. So we're going to be looking at another subset of R. So we looked at the subset omega of the state space. And then inside of omega, we looked for R. And then inside of R, we looked for M. If we can show that M is the largest invariant set in R, and by invariant set means if we start in this set, we always remain in it, then this is the proof. This is the statement of this theorem or this result. If M contains only the equilibrium point that we're interested in, which means that M is a set that consists only of 1 point, then we have a proof that X star is locally asymptotically stable. Not even that, not only that, Lassalle's invariant principle gives you something even better. It also tells you what the domain of attraction is for this equilibrium point. And this domain of attraction, we call it omega L, is all of the points inside of this set omega, such that V of X is less than some constant L. Any questions? Very abstract, a lot of sets. Let's look at an example. Yeah. Any questions in this abstract definition? Yes. Yes. We need it to contain the equilibrium point only. In general, it will have more points. V dot equal to 0 will be satisfied in general by many points. You can have infinite number of points. If we can do something or show that only M contains one point only, which is the equilibrium point, then we can guarantee that this equilibrium point is locally asymptotically stable. Actually, by Lassalle's invariance principle, so again, just to be precise, this result that's mentioned in this case is actually attributed to Barbashin, Krakovsky, and Lassalle. Krasovsky, okay, and Lassalle. So these are three people, okay, that contributed to this result. Lassalle's invariance principle by its own is only this part. What he proved is that if you have V and V dot to be such, V is positive definite and V dot is negative semi-definite, and you have the set of V dot equal to 0, what Lassalle showed is that if M is the largest invariant set, then we always, whenever we start inside of omega, we will go to M. Okay? We will always go to M. There is an intuition behind it. I'll just give you the intuition behind this. Of course, not the formal proof, but just the intuition behind this result. I know that V is positive, right? So it has like the shape of this bell, right? So this bowel, sorry, right? And V dot is negative along the trajectories. Means that at every time step, what will happen to the value of V? It will decrease. So if you start with some positive, some value of V is equal to 2, the next time step, what will happen? It will decrease because V dot is less than or equal to 0, which means that the next time step, I'll either be negative, I'll either decrease, or the V will either decrease or will remain with the same value. The time step after, decrease or remain with the same value, decrease or remain with the same value. So you see, we're going to be, after some while, we're going to be reaching a big set in the state space, and this set is M. That's it.
Already know that the system is stable.
Yes.
So we are already knowing that we are converging to that point.
No, this is not what stability is. Stability means that if I start near that point, I remain near to it. So stability means I'm not going away from that point. And I don't know precisely what this area. So you remember what we discussed with Lyapunov's direct method. It doesn't tell you anything about this area, where exactly where you start and you go away from that point or near to it. This is a more powerful theorem in the sense that it tells you, it's talking about the sets where we're starting. Which function? V. Okay. Yeah, exactly. It's asymptotically. Yeah, of course. Yeah, exactly. Everything is asymptotically. Yes. So as t goes to infinity, we know that V is going to be decreasing to some value up until we reach this set, and this set is given by V dot is equal to 0. Now this set can contain an infinite number of points. And the extension, okay, that if we have the case that M contains only the equilibrium point, then we have a proof that we're going to be reaching, okay, the set M that contains only one point. What is that point? It's our equilibrium point, and this is the definition of a local asymptotically stable. Let's see it in practice. Okay, we're going to be, first of all, we're going to be applying Lassalle's invariance principle to technically everything we do from now on. Okay, and it's always going to be along the same line that we're going to be doing. And usually, Who here saw this in some paper once or one? Only one? You don't need a lot of papers, okay? So you need more papers. I would say I'm not going to put a number, but in a large percentage of papers, you're going to find the Salle's invariance principle stated as like something in one line, okay? Because it's very fundamental. You can always construct it this way. What I'm going to do here is really all of the details about it in a very simple example, which is our pendulum. You have a question, Mark? I'm going to come to that in the end. I'll summarize that in the end. But let's look now at this example. This is the pendulum case, the state space model. We have this nonlinear system. We showed earlier that we had two equilibrium points, the one downwards and the one upwards, statically, not moving. We have V of x given by the kinetic energy plus the potential energy. And we showed earlier that V dot is equal to minus C2 x2 squared. Is this a negative definite or a negative semi-definite function? Said it's negative semi-definite because it doesn't contain x1. Last time we wrote it in this as a quadratic function, and we saw that indeed we have zero eigenvalues. So by Lyapunov's direct method, I can only conclude it's only stable. Now let's see how do we apply Lassalle's invariance principle. The first thing is that if you go back to the whole setting of Lassalle's invariance principle, it tells you start with some neighborhood that contains the equilibrium point. So I don't have anything to start with. What is the best thing? If I don't know what this neighborhood should be, what should I start with? I start only with one equilibrium point that's very restrictive. I need some neighborhood of the equilibrium point. What can I start with? Everything, exactly. You start with the whole state space. Let's start with the whole state space and see what happens. So let's start with omega being the whole state space. We know that V dot is equal to this equation. Always keep that in mind. And we know that V is given by this equation. So let's define the set R that has all of the points in the domain omega, which is the same as the state space, that has V dot is equal to 0. What is this domain? Again, looking at the function that we have, the function that we chose, and the V dot that we calculated earlier. What is the set R? How is it defined? When does V dot satisfy when is V dot is equal to 0? For any value of x1 and x2 is equal to 0. So if I have x1 equal to any number and x2 is equal to 0, then I immediately have V dot is equal to 0, which gives us this definition of R. Of course, that's why I'm saying this is a further analysis after you do Lyapunov's direct method. And then you reach the bottleneck that this is negative semi-definite. So I cannot conclude local asymptotic stability. Okay. So this is the set R. What do we do next? Anyone got that? We get the M. We get the set M. What is the set M? The largest invariant set inside of R. By largest, again, we're going to see what the term largest means, but we're talking about sets here. So when I say I have one set and another set and another set, the largest of all of this is just the union of them. Okay, so I take all the union of all of these sets, and then combination of all of this is the largest set. Okay, so this is in the set theoretical manner. So now let's look at this set R. All of the points X that will start in R and have x2 is equal to 0 and do not change will have x2 dot is equal to 0. Okay? In other words, it's as simple as take the time derivative of this condition. That's it. If the time derivative of this condition is equal to 0, this means that I'm starting in a point inside of R and I'm not going to change. I'm going to stay within that point. So points that have, so the invariant set in R will contain all of the points that satisfy the rate of change of x2 is equal to 0. And x2 dot is equal to 0. If I go back to the dynamical equation, I see that I should satisfy that this expression is equal to 0. I'm already in the set R, which means that x2 should also be 0. So I'm left only with one equation, which that sine x1 should be equal to 0. We already actually calculated that before. We know that all of the points in the state space that satisfy sine x1 is equal to 0 are the equilibrium points. So what is the set M? The combination of the equilibrium points. It's a one set that contains 2 points. It's given like this. So can we directly conclude Lyapunov as local asymptotic stability for this equilibrium point we're interested in? Exactly. We said M should only contain the equilibrium point we want. Here it contains 2 points. In general, it can contain more than that. Exactly. This is precisely what you do. We started by omega being the whole state space. Now let's try to do something smart by restricting omega. So we're looking at the whole state space. Let's try to look at smaller set. You can play around with this. Okay, what number do I start with, or how do I restrict the domain? By looking at the level sets of V of X. Substitute V, okay, substitute the first equilibrium point in V, and substitute the second equilibrium point in V, and see what numbers do you get. If we substitute the first equilibrium point in V, we get 0. If we substitute the second one, we get 2C1. What does that tell us? Again, V is we said that it's a function that looks like this, right? We plotted it last time, I remember. It's a function that looks like this. It also has some sort of like curvature, okay? But it's a bowl-like function. If we consider the whole state space, we're going to get these 2 equilibrium points as the invariant set. If we only constrain V to be, we know that V at the equilibrium point, which is the 0, 0, the one that's downward, has a value of 0. And that makes sense. It's a minimum. Up to where should we stop with the values of X? Just before 2C1. Because if we take 2C1 and higher, it's going to be including what? The 2 equilibrium points. So if we restrict ourselves in a domain that's just less than 2C1, in other words, if we refine omega to be given by this omega with a subscript of 2C1, which is defined as all of the points X in the state space that satisfy V of X is less than 2C1, and we refine R to be all of the points that live in this smaller domain. This is not the whole state space. This is just a smaller domain. Then the largest invariant set in R becomes only one equilibrium point, which is this one. And thus, using Lassalle's invariance principle, you can show that any solution that originates in this region that we chose, that we restricted ourselves, will tend to X1 star. And thus, we concluded that it's locally asymptotically stable. Hooray. Okay. This is very intuitive, by the way. We always said that, I know that, okay, physically we know that the downward position is stable, and the top one is what? Is unstable, okay? So what we exactly do is that we choose the X, the capital X, which is our state space, to be all of the state space except for what? Except for the one on the top. How did we know that? We did that. How did we know how to restrict it? How to do what helped us to do that is the Lyapunov function that we chose. Okay, so we took all of the energy levels. Okay, we took all of the points that satisfy energy levels that are less than 2C1, which includes the point that we had, okay, which is the one on the top. So now we're left in a domain. If we start in any of these points, and by the way, this includes the whole circle, up to what? Just before the point, so it includes all of the points, up to except the one that's on the top, the one that's equal to theta is equal to pi. So I excluded that. And then I know if I start with any one of these, what happens? I'm gonna converge. Okay. Yes.
So when we conclude, if we initially didn't restrict M, we got, the omega, we
Yeah.
got the full state space, and we don't get any equilibrium points in M, then it's just stable. It will not be asymptotically stable.
You don't get any equilibrium points?
No, two of the equilibrium points.
Yes, that's right.
It's not particularly that we get them. like we can follow can we follow the steps?
Yeah.
We find that M doesn't satisfy that has the equilibrium points.
It doesn't have the equilibrium point in the first place. It would. Okay, so you're saying you want to conclude instability now.
We previously know it's stable.
Yes.
I mean, this principle comes to M when we don't have equilibrium points. What is this case for? Like,
Oh, okay. So M is in R, and R is in omega. And omega is one of the regions where we know that includes the equilibrium point. So the equilibrium point, if we start at it, we'll always stay there. So the equilibrium point has to always be an M. So that's just a very quick proof that you can never get an M that doesn't have the equilibrium point.
you get semi-definite function, the function, the second part is asymptotically stable. I'm trying to relate when I reach to this point in the Lyapunov.
So
What are the conditions?
up till this condition, we already have Lyapunov stability. That's right. But we also include in omega the equilibrium point.
So we initially, anyway, start with the equilibrium point inside omega. Or
Absolutely, absolutely. You're always, again, you're always trying to assess the stability of an equilibrium point. And the first thing to do is that V is positive definite in a region that includes the equilibrium point, not everywhere. I always need to start to have that V, our first condition, if you go back, it was that the V at the equilibrium point is equal to 0, which means that I'm already at a local minimum. And this means I'm already in a positive definite region. The V is positive definite in the region that includes the equilibrium point. Any questions? Which one? What Ziad was asking about is that can we follow this process and then reach an invariant set that doesn't include the equilibrium point? And the argument is no. Okay, we can never have that. We already have an invariant set in the domain, exactly, that includes all of the equilibrium points. But by the way, this is very easy because you have only 2 equilibrium points. If you have 10, you're going to have 10 equilibrium points. You can have more nonlinear behavior. There's something called in nonlinear systems a limit cycle. And limit cycles are usually when you have periodic motion that's stable or unstable. There's something more complicated. You can have also, so nonlinear systems are much more complicated than this. Okay, so we don't have we've never seen anything with limit cycles. We will not see. But again, if you take any course on nonlinear systems, if you dig in deeper in that, you're going to find that there are more complex phenomena, and you might have a combination here inside of M to have equilibrium points and limit cycles and more stuff. Yes.
I mean, based on going back to the question that you asked, doesn't it seem now that it's always a trivial solution that we get that exact set that contains just that particular.
If we do this restriction, yes, of course, and that's why it's a very fundamental result. How do you prove asymptotic stability?
I mean, we can always restrict it to always include.
Absolutely, yeah. If it's asymptotically stable locally.
I mean, technically speaking, we know it's stable.
That's right.
But then what we're trying to prove is local
yes.
Stability. So isn't it always possible for us to prove that?
Yeah.
No matter the case scenario.
If it's truly locally asymptotically stable.
So
if it's not locally asymptotically stable in the first, so in other words, can you try to do the same for the other equilibrium point and reach the same conclusion? It's impossible. We already know from Lyapunov's indirect method it's unstable. So no matter how hard I start, okay, with other Lyapunov functions, I'll never be able to do that. That's the idea.
The alternate question now is for global asymptotic stability, can we still reach the same conclusion?
Yes, provided that the domain is all of X, not just a subset of X. If I can do that with my Lyapunov function being locally positive definite in all of X, and I know if I start anywhere in X, I'm going to reach the set R and then the set M, and the M contains only one equilibrium point, then I've proven globally asymptotically stable. If you can do this for all of X and exclude just the equilibrium points, the other equilibrium points. So this is an example that we have here, that M is given by only the equilibrium points of the system. And I've just excluded one equilibrium point. This means actually that I have here, and I can, we need to show that this is, what was it called? Readily unbounded, and it is readily unbounded, okay? Which means that we've already had a global asymptotic stability, but it's not really globally asymptotically stable. It's this case where I said it's almost globally asymptotically stable if we exclude this one, okay?
Shouldn't the unique case or what you are trying to get be the case where it's globally asymptotically stable? Because if we can almost always prove the local asymptotic stability.
If it's truly locally asymptotically stable.
I mean, if it's stable, there are two choices. It's either local or global.
Yes.
So if we can always.
No, sorry, what did you say? No. You can have something that's stable and it's not locally asymptotically stable. An example of that is what we looked at for the satellite. For the satellite, we've only been able to show that the origin omega is equal to 0, 0, 0 is only stable, but no matter what we do, we cannot show local asymptotic stability. It's physical. We know from the physicality of the satellite example, but we cannot show it with any Lyapunov function. Keep on trying forever.
But then we know it's stable.
Yes.
Exactly.
Okay.
So now we know it's stable, but in terms of stability, we have how many options? If we were to, deeper, how many options would we have?
A lot. Not just stable, asymptotically stable, and not just local asymptotic stability and global asymptotic stability. You have much more than that. Exponential stability and finite time stability.
But then exponential stability is also a form of global stability. Right?
No. That's off topic. Never talked about it. Never will. Off topic. We can discuss offline. Okay. Any more questions? Okay. So as a summary, okay, for how do we apply Lassalle's invariance principle? You start with the Lyapunov's direct method. If you have V dot is negative definite, you conclude asymptotic stability of that equilibrium point. If you only have negative semi-definiteness, move on further. Try to find the set R where V dot is equal to 0. And then you must check whether, if I'm in R, again, by doing this further analysis of the system, if I'm in R, there are some regions where I'm always going to be staying there, the invariant set, and then you can conclude you always go to this invariant set. If I can show extra that this invariant set has only the equilibrium point I want, or if I can smartly constrain the state space or the domain I'm looking in, then I conclude asymptotic stability of the equilibrium point. Now let's look at very nice, this is too technical, let's go back something very nice, PD control. Who here loves PD control? I personally love it, Proportional derivative control. So let's look at let's revisit PD control on R3, something you all know, it's trivial, you can do it with your eyes closed. So let's look at first at the Euclidean space Rn. The governing equation of a point mass, no gravity, is the rate of change of position is equal to velocity. The rate of change of velocity is equal to 1 over m multiplied by the forces. U here is the control forces we're interested in designing. So we can write it in a state space form that looks like this. Psi dot is equal to, so x dot is equal to f of x plus gu. G here is given by this matrix that's multiplied by the force, and x here is just a function of v. We don't have any potential energy, we don't have any gravity energy, we don't have any springs or anything, it's just a point mass floating in the air. Then we have this equation. Just as a side note, because we're going to be needing that later, that this system is just a point mass that's floating in the air. It doesn't have any potential energy, but it has kinetic energy because it's moving. How is this kinetic energy calculated? Half mv transpose v. We're going to be writing here, we're going to be choosing the state for reasons going to be clear later. We're going to be choosing the state, not psi and v. We're going to be choosing them as psi and p, the momentum. And momentum is simply mv. M is a constant, so m multiplied by v. If I take p dot is equivalent as mv dot. What is mv dot equal? Is equal to u. So mv dot, the rate of change of momentum, is equal to forces, Newton's second law. So the half mv transpose v, I can rewrite it as 1 over 2m p P transpose P. This is just the kinetic energy rate in terms of the momentum instead of the velocity. Easy? Yeah.
The number of cases where we can have the mass of the robots changing, for example.
Next week. Okay. So the PD control of a point mass. Our goal when we want to design a proportional derivative controller, a PD controller, is to stabilize the system at some desired state. By stabilization means I'm not going to be doing any tracking, which means I only have one configuration I want to go to. This is psi d, okay, with a velocity of 0. So I want to go there and stop. I don't want to follow a circle or a trajectory. I just want to go to that point and stop. So this is the position and this is the velocity. How do we, again, write a classical PD controller? Simply, we define the error between the position, the actual position and the desired position. And then we multiply this by a gain Kp and a gain Kd to its time derivative, which in the end, by, again, just substituting what the values are, what the definitions are, we get this equation in the end for the control law. So U is equal to minus Kp of psi minus psi d, and then I have minus Kd multiplied by V. If you look at this form, you see that the control law, U, is a function of psi and V. And what are psi and V? The states. Again, V is the state. V is equal to P over M, so it's still a function of the state. So you see when we earlier mentioned that when we talk about the closed loop system, we already chose U to be a function of X, and then we plug it in. If we plug in y of X, the gamma of X instead of the U, if you look at this equation, X dot is equal to f of X plus G gamma of X. What is everything on the right-hand side? A function of X that looks like this, and this is our closed loop system for an example. So here we're not looking only at an open loop system. We have a closed loop system that we already chose what the control law looks like. We plugged it in. We reduced it. We did some simplifications to write the system in this form. The question is, can we guarantee? So we said that I have a PD controller. I know what the controller looks like, and I want the system. So I want X to converge to X desired as t goes to infinity. In other words, I want to have this as an equilibrium point of the system. Do I have that? How can I show that for this system? Again, use Lyapunov's direct method, Lyapunov's indirect method, and so on. This equation written in this way is actually a linear system. Everything is linear so far. So it's trivial how to do it, right? If you took a multivariable linear course, so this is, you can prove the stability by calculating the eigenvalues of A minus BK. Okay? This is exactly what's inside of here. We're going to be doing it later with Lyapunov's method, okay? Just to practice. PD control, easy, okay? Let's do a PD control of a manifold, on a manifold. So let's look at the satellite problem. And the satellite problem, last time we looked at only at omega, right? Because it was just rotating and we didn't have any orientation I want to go to. Let's assume now I want to stabilize the satellite to some desired orientation and to have it not to rotate. So I want to have R equal to R desired and omega equal to 0. Just a very simple extension to what we discussed of the point mass. So this is our state, R and omega. R lives in a manifold, SO3, and omega lives in a vector space, which is related to the Lie algebra of the Lie group SO3. So first thing to do, error, matrix, error, matrix. Derivative of the error matrix. Does that work? How many violations do you see? A lot. A lot of geometric violations. What's the first one? I cannot calculate the error simply by R minus RD. Why not? I don't have a vector space structure. Have you proved that before? Many times. Okay, so I don't have a vector space structure in SO3. What about ER dot? ER dot, if I take the time derivative of the error, assuming that the error is correct, or of that state, I get that the error is R dot. And R dot lives in a tangent space. It's a vector space, that's nice, but it's a tangent space to some R. Then what is Kp and Kd now? Are they matrices? Look at the right-hand side. Everything on the right-hand side, this is a matrix, 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 matrix. How can I convert all of this into a vector, or in other words, a covector? Because this is the torques that are applied to the satellite. Does this work? Okay, don't try. Okay. The next best thing, okay, which actually the worst thing you can do with, if this is only your knowledge, is to go to Euler angles. So transform the R into Euler angles. So I'm going to have a roll, pitch, and yaw actual, roll, pitch, and yaw desired. Take the difference between them, multiply this difference by a gain, multiply the errors by another gain, and you're going to get a PD controller. Will it work? Okay. Inshallah, it will work. Okay. Very good. That's the spirit. It will work, but locally. Again, very, very tiny. Okay. Because definitely this is not what we're going to be doing. The first, how do we extend the PD controller to the manifold case? We're going to reinterpret the PD controller as what it does to energy. Okay. Who here heard before that or knows that a PD controller is nothing else? I can reinterpret it as the gradient of some potential function and damping. Good. Okay. So let's reformulate PD control on R3. We're still on R3, but we're going to be doing all of this preparation because this extension or this generalization of the PD control to R3 in this new language or in this new way will allow us to extend, not easily, but will allow us to extend to the case where we have a manifold. So the proportional term and the derivative term, which are in the case of R3, were given by this, minus Kp and the error and minus Kd and the error dot, are actually two terms separately, and they have different interpretation. We're going to be interpreting them differently. The first one, which is the proportional term, we can interpret it as the gradient of some potential function psi. The result, we know that we need it to be minus Kp multiplied by the error. But this psi, if we choose it to be half psi minus psi d transpose Kp psi minus psi d, what is the shape of this function, this psi? What does it look like? It's a quadratic function in Rn. Okay. So it's a quadratic function that has the Kp and it's like located at, it's shifted with psi d. What?
The same as kinetic energy?
No, not the same, not that much. Okay, but looks like it. The kinetic energy is also quadratic, but this is in terms of the position. So this is a quadratic function in terms of the position. Have you seen something like this before? I'm pretty sure yes. What? So what kind of equation have you seen this before, and for what mechanical system? For a spring. The potential energy of a spring is half delta x transpose multiplied by k delta x. And what is the force that corresponds to the spring? Is equal to minus the gradient of that potential function. So this is exactly what we see. So the proportional term is minus the gradient of this potential function psi, and this is the function psi. Psi, in the way that we chose it, is a globally positive definite function of okay, sorry, I need to be precise in the linguistics here. So capital psi is the function, and so capital psi, okay, and this is the psi, which is the position. So hopefully the context will make sense. So but this is just an extra, 1 second, okay, this is just an extra addition, right? So looking at the proportional term as the derivative of some psi. Not only it will allow us to extend to the to a manifold case, but it will also allow us to do Lyapunov stability, with direct Lyapunov stability. So we can always choose the Lyapunov function to be the sum of the psi, this potential function that the proportional term comes from, and the original kinetic energy of the system. In our case, we had only kinetic energy. If we have potential energy in the system, we can add more terms. But for our point mass, it was only a point mass moving in space, which has only kinetic energy. So this is the kinetic energy, 1/2m p transpose p. And the psi here is given by this expression. So we can choose this as Lyapunov function. Let's see what happens when we try to do v dot. First of all, before calculating the v dot, this is a quadratic function, and you can show that its Hessian is given by this equation, okay, this matrix, and it's clear that is positive definite. It's globally positive definite because this is a quadratic function. It means as p increases and as psi increases, you always get higher and higher values. Okay? There are no nonlinearities here. This is just a quadratic function. So if you calculate the Hessian, as I showed you last time, you can get this 6 by 6 matrix, and you can show that it's positive definite everywhere, which means that this is the v of x is a globally positive definite function. Now let's calculate v dot. So x had was 6 numbers. So x was psi, 3 numbers, and p, 3 numbers. So psi dot is 6 numbers. The dv of x, which is the differential of the Lyapunov function, is a covector. It's a 1 by 6. So this is 1 by 6, and this is 6 by 1. So this pairing on R6 is simply multiplying a 1 by 6 vector multiplied by a 6 by 1 vector. V is the sum of 2 terms. So here I write v of x, and I have 2 functions inside of it. The first one is a function only of the first state psi, and the second one is only a function of the second state p. So I can write the dv of x as the d capital psi of small psi dot, plus dh of p dot. Okay. Then we know that, okay, this I can write it as a vector again. So here I'm going to just use the vector so that it's easier in terms of display. So this gradient is if you remember, this is the vector version of this covector. So the gradient written with the nabla is the vector version of this covector. So this multiplied by that. This is 1 by 3, and this is 3 by 1. Or I can write it as 1. I can transpose this 1 by 3 multiplied by 3 by 1. And I'm going to write the covector version of this. Sorry, the vector version of this multiplied by p dot like that. By the way, the result here is a scalar. So when you transpose it, okay, it's the same value. So you can always go back and forth. I can rewrite this as p dot transpose multiplied by this without the transpose. And I can rewrite this as this transpose multiplied by this without the transpose. You can always do that. Psi dot is equal to v. P dot from the dynamics, we have it there. P dot is given by, we had it, P dot was equal to u, and we chose u to be equal to up plus ud, and we chose up to be equal to minus the gradient of psi. Take a look at what happens here. What happens immediately? They cancel out. No matter how nonlinear, right? No matter how complicated psi is, okay, it will always cancel out in this way. So we didn't just generalize a PD controller. Okay, this is very powerful because it allows you to choose any function, not just the quadratic one, to get a proportional controller is equal to kp multiplied by the error. You can choose any psi and choose u to be, okay, the gradient of it, and you're going to be seeing, you're always going to reach this end in terms of the Lyapunov analysis. UD was the derivative term. We haven't chosen it yet. Okay, so we left it open. We haven't chosen the UD yet. Does anyone have any guess of UD to make v dot less than 0? What? Minus k v. If you choose UD to be equal minus kv for any k, for any positive definite k, what happens? Okay, you're going to get negative semi-definiteness. Okay, so if I use UD is equal to some matrix minus some matrix multiplied by v, I've shown that v dot is negative semi-definite. Why is it negative semi-definite? What's the easy check? What? Why is it not? Why is it less than or equal to 0? Where does this equal come from? What is the easy check? How do you look at it and say, yes, it's definitely negative semi-definite? It doesn't contain the psi, right? Remember when we had the pendulum and we calculated the v dot, and it was a function of only of x2, not x1. Then we concluded negative semi-definiteness. This is exactly the same. So here I calculated v dot. I don't have anything related to the psi. Why is that? because everything related to the psi, what happened to it, was canceled out when we calculated the proportional term. So you see the proportional term comes from this part alone, and the damping term is related to the V alone. And in this case, I have it's negative, so it's always increasing, but I don't have a function, it's not related to the psi, so it's negative semi-definite only. Up to here, what do we prove? Stability only. How to move further? Lassalle's invariance principle. And you can show that we actually have a globally asymptotically stable. Why is it globally asymptotically stable? Because if we go to the psi here, if you look at this V that we chose, which was equal to the psi plus the h, it's radially unbounded, okay? While p goes to infinity, v will go to infinity. While psi goes to infinity, v will also go to infinity, right? So as the further you go away from the origin, the bigger v will be. So we actually have this quadratic function that's about everywhere. What do we have? Okay, so this is the summary. So you can always do, so what is proportional and derivative control? You always start by this process. The first step is that you say U is a sum of two terms, UP and UD. One which will act as the proportional term and one which will act as the derivative term. The proportional term is actually an energy shaping term, and the derivative term is actually a damping injection. So we used UD to only inject damping to make the system, instead of being stable, locally asymptotically stable, while the UP will shape the total energy of the system, the closed loop energy of the system, such that the minimum is at the desired place we want to be. Then what you do next is that you choose some locally positive definite function, psi of capital psi of psi, designed such that psi d is a minimum. So we always have to check whether psi d is a minimum of this function or not. Let's go back here. This function that we chose here, where was it? This one. When we plug psi equal to psi d, what do we get? We get 0, right? So at psi equal to psi d, you get here 0 transpose kp is 0, which the value is 0. And if you go a little bit away from psi equal to psi d in either direction, in any value, you're always going to get a positive value. Okay, this is just a quadratic function, okay, as a function of psi minus psi d. Okay? So this is equivalent to half mv squared in the 1D case, or half k delta x squared. So if delta x is any positive number, the half k delta x is always a positive number. This is the multivariable case of it. So after we do this, and we choose UP to be the gradient of this capital psi, we can choose UD to be any nonlinear function. This is the best thing about this. We can not just choose it to be minus kd multiplied by the v. We can have any nonlinear function of v, such that v dot is negative semi-definite. So you can design this as you wish, and you can design this as you want. You have full freedom, not just some kp multiplied by an error and some kd multiplied by an error. We still have a PD controller, but it's much more general than the one that we started with. And if we have v dot is negative semi-definite, what do we do next? We do Salle's invariance principle, and we can show that xd, which has that the velocity or the momentum is equal to 0, and psi is equal to our desired point, that we designed to be the minimum of this capital psi. We have that it's a locally asymptotically stable. If you can do one extra step, if you can choose psi not to be locally asymptotically stable, a locally positive definite function, but a globally positive definite function, then you can prove that this desired equilibrium is actually globally asymptotically stable equilibrium point of the closed loop system. Questions? Yeah.
We chose P way back as a state only for ease of calculation, or there are
yeah, only to simplify. And it comes in here. You see? First of all, there was no m. If you do it with the v, you're going to have m all over the place. Okay? If you generalize this, when you look at, for example, with the satellite case, you're going to have, instead of the m, the j. Right? And if you generalize this to the full rigid body, you're gonna have the generalized inertia matrix all over the place. When we work with the momentum, you see, everything is nice. That's any questions? More questions? Yes. As the proportional as KD as a gradient. Okay. This is the proportional term minus KP error. If you choose psi to be, let's say I tell you psi is given by this function. And I tell you take the gradient of this function. Okay. Calculate the gradient. How do you calculate the gradient? Partial derivative, right? What's the partial derivative of this guy? It's this is equivalent to half mx squared or half kx squared. So we take the 2, multiply by the half, and then you reduce the one order of the 2 to be 1, so you get in the end kx. So the gradient of this is equal to k of psi minus psi d, which is the error. And then I multiply it by a negative, and this is the kp. So you see here this proportional term, right? I can interpret it as the gradient of this function. If I generalize this function to be anything else, here I choose a quadratic function. If I generalize it to any other positive definite function, any other, and I choose the gradient, I'm gonna get maybe something nonlinear, but it's a proportional term. Yeah.
So like we've walked from the non-geometric state basically.
Everything here is still Euclidean, yes?
Yeah, and we are going to something more general.
Yes.
Right? But then you also mentioned also that if we take something, any function that's even non-linear,
Yep.
then we also get a PD control.
Yes. It's a nonlinear PD controller. That's right. Nonlinear PD controller on Euclidean space. So this, okay, to go back here, this is a linear PD controller. Okay? A linear PD controller. And I had a linear dynamical system. When I took the linear controller with the linear system, what was the closed loop system? Linear. I composed a linear with a linear, I got a linear system in the end. So this is A minus BK, something like that.
The whole point of calling it a PD control, like, why do we still call it a PD control then?
Because it's a PD control. It's a proportional term and a derivative term. This is what I'm trying to say. So PD control, you can interpret it in this way. It's not the linear PD controller that you put in your CV, or that is in your CV at this moment. Okay, this is a more advanced version of it. Okay, so this is not the PID controller that works for a process. No, we're not doing that here. So this is still a PD controller. It's a nonlinear PD controller. Okay, it's a very general one. Of course, if I choose the psi to be quadratic, and I chose this to be a linear, okay, minus KD, for example, multiplied by V, I recover in the end the linear PD controller we started with. But here, this process allows us to do it more generally. And by the way, without doing any proofs, this is a theorem that is very general, right? No matter what the psi is and what the capital psi and the small gamma here, no matter what these functions are, even nonlinear, highly nonlinear, we're still okay. We still conclude the local asymptotic stability of this equilibrium point. So we've boiled down, so no more analysis. This is just a general procedure. If you want to do control for any linear system, if you want to do PD control for any system, and you can follow this process, okay, then we have it. Any questions? Okay, let's try. We still have like 8 minutes left. We don't have time to go to the satellite case, so we're gonna have that on Tuesday, inshallah. But let's spend the rest of the time showing you how do we show using Lassalle's invariance principle that this is okay asymptotically stable. Let's try. Yeah. It's a good question. Let's see. So the question here, what happens to when we have multiple equilibrium points? So what will the proof that we did here, our starting point was I have a locally positive definite function that includes psi d as a minimum, which means that it is an equilibrium point, or it's a minimum of this positive definite function. So I've already excluded everything else because I'm looking only locally. And we've only, with this controller, I'm only going to be working locally. Okay. So far, it's only everything is local. Depending on how many other equilibrium points, let's say, for example, just as an example, you have 20 equilibrium points. One of them is only that satisfies this local positive definiteness. This is the only one that you're interested in. Okay. Usually it's the origin. And the 19, the rest of the 19, the rest of the 19 equilibrium points are all unstable. Then what do I conclude with this controller? It's a globally asymptotic, it's almost globally asymptotically stable. Why? Because in the end, I have only 20 equilibrium points. 19 of them are unstable, which means if I start near any one of them, I'm going to go away. And then I showed that I'm going to go in the end near one. Okay. And then I'm going to reach it from any place in the state space. So this is an almost global asymptotic stability. So again, what this function will be locally positive definite in some neighborhood. But in this case, if I take the whole state space, it will be positive definite in everywhere except at the other equilibrium points. So I can just exclude them in the way that we did. Okay. Can we always, okay, I'll come back to that, to your question, Pansy, but one more comment. So here, can I always find a globally positive definite function? What prevents us from finding a global positive definite function? No, I'm talking about the psi itself, before even talking about Lassalle's invariance principle. Can we even, okay, sorry. So this psi here, can we always, I'm saying we can find a locally positive definite function. Can I sometimes try and harder and try to find or design another one that's globally asymptotically, that's globally positive definite? Let's say you don't have multiple equilibrium points. Is there something that would prevent us? The answer is yes. The topology of a manifold can prevent you from having something like this. Now we're going to be getting something very deep. But this is just as a side note. So there are some manifolds that it's physically, it's not geometrically impossible to construct on it any globally positive definite function, which leads with this result, which means that I can never design a globally asymptotically stable controller, no matter how hard I try. Okay. What? For some particular manifolds. One of them is S2. So one of these manifolds is S2. So if you're unlucky to have any mechanical system that lives on S2, you cannot design a globally asymptotically controller. Okay, only locally. Now let's look at, okay, no time to go into details of the proof, but let's just try to work out the sketch of it. So how do we show this part, which is using Lassalle's principle that this is a globally asymptotically stable point? So here we have V dot. So we did, first of all, Lyapunov. We have the V that's positive definite everywhere. We have the V dot that's negative semi-definite. What was the next step? We said we wanted to calculate which set? R. So R, the set R, should have all of the points that consist of psi and V, or psi and P, that satisfy what? That satisfy V is equal to 0. And if V is equal to 0, we have that momentum is equal to M multiplied by V. So what is the momentum? So it's also 0. So the condition, so R consists of all of the points where all of the positions with V is equal to 0. And thus momentum is equal to 0. Let's look at the time derivative of V dot, which is equivalent to P dot over M. Okay, so if V is equal to 0, so V dot should be also equal to 0, which means P dot should be equal to 0. If we go back to the dynamical system, and here we have to go back to the system dynamics. Actually, maybe let's go back here to the general case. So if P dot is equal to 0, then I should have here, okay, and first of all, the UD will be cancelled. Where is it? So the UD, I've chosen it to be minus KD or minus some function of V, and the V is equal to 0, which means this will also disappear. So I'm only left with the values that satisfy the gradient of psi is equal to 0. I designed the psi to have only one minimum at psi equal psi d. So we designed the psi to have a minimum. What does a minimum mean? It means if I take the gradient of this, okay, it should be equal to 0. We designed the psi to have the gradient at psi equal to psi d. So if we go back here, so psi is equal, if you take the gradient of this, you're going to find it's minus kp psi minus psi d. The gradient at psi equal to psi d is equal to 0. So what is the only point that satisfies that's inside of the set R, that's an invariant set, is the equilibrium point 0 and 0. So M consists of only one point, 0, 0. R consists of all psi and V is equal to 0. And thus conclude by Lassalle's invariance principle that we have a locally asymptotically stable. But not only that, we also have that psi we designed it to be radially unbounded. It's globally positive definite. And thus we conclude global asymptotic stability. And that's it for today. So all of this is a preparation for going on the satellite. Okay, 2 days, inshallah. Okay, any questions? جزاكم الله خير. سبحانك اللهم وبحمدك. أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.